we have a particle whose position vector is given by the vector r. Here omega is a constant and t is a parameter. Now, in the first part, we have to show that the velocity of the particle is perpendicular to vector r. Let's begin with part 1. So here we have our position vector r as a function of time given by cosine of omega t I cap plus sine omega t j cap. So let this be equation number 1. To find out the velocity, all we have to do is find out the time derivative of our position vector r. To take the time derivative of the position vector r means we have to take the time derivative of each of the terms on the right hand side. But I cap and j cap, these are constant vectors, they're constant unit vectors. So that means if we take the time derivative of I cap, that will be equals to 0. And this also holds true for the unit vector j cap. So that will mean we will only have to take the time derivative of their respective components. So let us begin. Now time derivative of the cosine function is negative sine omega t, and we'll also need to multiply to omega, which is arising as a consequence of applying the chain rule here. This is I cap plus taking the derivative of sine omega t will be omega cosine omega t j cap. So this is equation number 2. Now what we'll have to show? We'll have to show that the velocity of the particle is perpendicular to r vector. If that were to be true, then the dot product between r vector and v vector, that means the first derivative of r with respect to t, this must be equals to 0. So let's show that. So that means we have to take the dot product between 1 and 2. So we'll have cosine of omega t, that's multiplied to negative sine omega t times omega. So this will be negative omega times sine omega t times cosine omega t. Plus we'll have to take the y component of equation 1 and multiply to the y component of equation 2. So this will be omega times cosine omega t times sine omega t. We see that both the two cancels out, leaving us with the value 0. And since the dot product is equals to 0, so we can say that our position vector r is perpendicular to the velocity vector. So this proves part 1. So let's move on to part 2. So let's begin with part 2. We'll first determine the acceleration. So acceleration vector that can be defined as by taking the time derivative of the velocity vector v of t. We have already obtained the velocity vector in the previous problem, so we'll use the result. So derivative of the components of the velocity vector, that will be, so we have omega times negative sine omega t, so that will becomes negative omega squared cosine of omega t I cap, plus we have omega times cosine omega t, so its derivative with respect to time will be negative omega squared sine omega t j cap. So this is going to be our acceleration. Now if we take negative omega squared as the common factor, so this will leave us with cosine omega t I cap plus sine omega t j cap, and this is actually the position vector r. So that means we have our acceleration vector, and this is equals to negative omega squared vector r. Now this negative signs tells us that the direction of our acceleration vector is opposite to the direction of r vector. So that means the acceleration is directed towards the origin. Now we'll also find out its magnitude. The magnitude of our acceleration vector, so that will be equals to negative omega squared r vector. So that means we have omega squared r. So this is the magnitude of our acceleration vector, which says that its magnitude is proportional. Since omega is a constant, we can say that our magnitude is proportional to the distance r from the origin. So we have proved part 2 as well. Now let's move on to the third part. So in part 3, we have to show that the cross product between the vector r with its first derivative over the velocity vector is a constant vector. So we already obtained these two results in problem number 1. So let us begin. So we will take the cross product between vector r and the velocity vector. So we'll use 3 by 3 determinant. So in the first row, we have the unit vectors I cap, j cap, and k cap. In the second row, we have the components of vector r. So that's cosine omega t, sine omega t, and 0. And on the third row, we have components of dr over dt. So that will be negative omega sine omega t, and we have omega cosine omega t 0. So we will expand these unit vectors along the first row. So here we will only have the components of vector k. So that will be k cap multiplied to, so cosine omega multiplied to omega times cosine omega will be omega cosine squared omega t, minus we have omega sine omega t multiplied to sine omega t. So that's omega times sine squared omega t. But since there's a negative sign here, this will become positive. So we have omega times sine squared omega t. So if we take omega as the common factor, so we were left with cosine squared omega t plus sine squared omega t, which is a identity with a value of 1. So we have omega times k cap. So k cap, that's a constant unit vector. Omega is a scalar, which is a constant. So that means the cross product between vector r and its first derivative with respect to t is a constant vector.